Good afternoon, everyone, and welcome to the new edition of Science Cafe, Austria-Serbia, which is organized in the cooperation between the Center for the Promotion of Science, Belgrade, and the Embassy of the Republic of Austria, Austrian Cultural Forum, which is held here in Belgrade. So this time, it will be organized in the cooperation with CPUS, which is a network for student exchange. So the abbreviation is CPUS, Central European Exchange Program for University Studies. Actually, we are hosting or coordinating one of the largest networks. Professor Đerić is our coordinator for the network called Euro Geoscience. So all of them invited us here. My name is Vladica Cvetković. I'm professor of Belgrade University in Faculty of Mining and Geology. So I will be moderating this event. And we will start with my pleasure to announce our invited speakers for today. Our special guest from my side here is Hans-Jirgen Gavlik from Mountain University, Leoben, and Professor Nevenka Đerić, professor of the University of Belgrade, Faculty of Mining and Geology. So they will give us a talk in their own combination. Who will start, who will then continue, that we will see. It will last some 30 to 40 minutes, and then we will be asked to join the conversation. I have some questions in advance, but I hope that you will have also. And the title for today is The Global Change. What can we learn from the last 250 million years of the Earth's geological history in this region? So I, again, have pleasure to ask you to give your talk. Thank you.
Okay, thank you. It's okay. I don't like microphone, but they said that I must do it. Okay, first of all, I want to thanks for invitation and also thanks for nice introduction. And can we start with our presentation with first slide? Because Professor Hans-Jirgen Gavlik and I will talk about the global change. Actually, we will talk about, okay, I need one hand more probably. No, okay. What we can learn from the last 250 million years on the Earth's geological history, it means we will talk about geology. And actually, usually people, when say global change, most of people think about rapid changes of the Earth system in the history of the Earth and their catastrophic impact on our biosphere, hydrosphere, and geosphere. Most of people actually talking about Anthropocene. It's still unofficial geological time. We use that time to describe time when human activity started to really have some kind of really catastrophic impact on our planet. But what is very important to say, the fact is the face of the Earth is changing permanently due to always ongoing geological and biological processes. And these processes mainly triggered by plate tectonics. Environmental changes are the response of climate change, sea level fluctuations, ocean circulation, as well as geochemical changes. And mainly, these changes is gradual. We usually say it's not really event. It means that we can see some changes in biosphere, but that's evolution. If happened that some species can evolve and die out, it's really extinction, but it's part of the evolution. It's normally for biosphere and for our planet. Okay, and when we say the main driving force are plate tectonic changes, actually we want to say that we have opening and closures of oceans and also mountain building process. We have oceanic and continental lithosphere, and that's our engine. The moving of this lithosphere is really Earth engine. And the Wilson cycle, it's actually base of plate tectonics. And what we know that this Wilson cycle describe that we have opening and after that closing, and it's repeat, opening and closing of ocean in geological past. And if we want to see which kind of stages we have, firstly, we call first stage Graben stage. It means ocean opening start. Next stage, it's oceanic stage. It means ocean is leaving. We have mid-ocean ridge with new oceanic crust, but also we have passive margins. And after that, ocean closing start. It means we will have active margin stage with collision or ophiolite abduction, which will be following mountain uplifting and unroofing. Unroofing, it means or erosion will start. Okay, this was story with gradual changes, but we also know that in the past happened rapid environmental changes, which we call events. It means that for these events, it's very necessary to have really short time. What does mean? We need that happened in very short time, but also how many species will die. It means the percent of species usually must be more than 75, and it must be happen very quickly. And if you ask who is guilty, usually if you read some more popular science text, usually you will read meteor impacts or volcanic activities. But to be in true and Cretaceous mass extinction, probably this meteorite impacts just was final touch. It's very important that we will have mass extinction. We must have several events, which is usually more important. What is necessary to have rapid environmental changes? I again repeat that it must be really quickly that environment can adapt and species can adapt for new environmental changes. And what we have, if we have volcanic eruption, we will have acidification of ocean. That kind of changing oceanic chemistry, it means that could be stop oceanic water circulation and also could be decreasing of oxygen, dissolved oxygen, and we will have anoxia events. That anoxia events it's not every time, but usually we can see in black shale deposits. Also, sea level fluctuation is very important for this kind of events. Okay, in the geological history of the Earth, such global changes with mass extinction appear from time to time, and because of that, geoscientists use the geological time scale to assign relatively age names to events and rocks, and of course, on that way, separating major events, and all this is based on the data which we have from rocks and fossils. And if you have rocks, you can really see that within the unique composition and arrangement of materials that compose different rocks, you can find patterns that are evidence of the process that formed. and also that form these rocks, of course. And if you are lucky, you can also find fossils. But fossilization is more likely to occur in marine environments. And also, if organism had hard skeletons, it's more likely to be fossilized than if had just soft tissue. But even if fossils are able to form, they may not be preserved because they must survive all later natural forces. Why we need fossils? We need fossils because they tell us age. We call that biostratigraphy. And for us, any kind of remains of organisms which lived in former ocean and seas, it's really, really terrestrial organisms. Any kind of remains for us is fossils. And we can find fossils in sedimentary rocks. But this is really games of chance. It means fossilization is really rare event. But we are very lucky because in Serbia we have a lot of sedimentary rocks. We have a lot of also founding of fossils, and this next talk we will follow by Hans-Jirgen Gavlik will be what we know from Serbia, which are our story, and what we know from our sedimentary rocks and fossils. Okay, you should go with our
You don't like to continue?
No.
It's a pity, no? I'm really relaxed between there and enjoy the talk, what you are giving us.
Yeah.
Okay, I will continue now, and we will have a closer look to our area, and this means definitively all these mountain ranges in the Mediterranean, and especially I will focus on the eastern Mediterranean mountain types, with special focus here on the Dinarites, where you have a large portion here in Serbia. And okay, it's written on the left side. This is also one very crucial part of the whole Mediterranean origin, and practically the whole last 250 million years geological history is preserved in the different sedimentary rocks in different depositional environments all over this mountain range. So in this Mesozoic time span, also in the Cenozoic, but I will focus on the Mesozoic, we have a lot of different turnovers in the history. In the Earth history, it means we see a lot of global changes which are recorded in the different sedimentary successions. So we see a lot of mass extinctions, over-regional events, and regional events. And the different questions are these really global changes triggered by something like meteorites? Are they triggered by something like large igneous provinces? We see here on the right side these red arrows, which show us several of these global changes. And we have to recognize, okay, everybody is talking about these catastrophic events like meteorites or rapid changes by large igneous provinces. But we know in the Earth history also a lot of meteorite impacts which triggered no global change. And also we have a lot of large igneous provinces, and we see, in fact, nothing. But we have also plate tectonic changes, opening of oceanic domains, closure of oceanic domains, okay, gradual changes, but sometimes they correlate very well with a global change. And then we have also the problem that we have some global changes which are definitively out of the focus by all of that. We always discuss the classical ones, which big five, and always we think also the classical system boundaries, like the Permian-Triassic global change, the Triassic global change, and we have the Jurassic-Cretaceous boundary, Cretaceous-Paleogene boundary. This has a special meaning. There is a global change. No, it doesn't. These global changes are sometimes not manifested in the time scale. And also this you have to recognize, not to oversimplify the stories. If we look in our area, in general, we see Wilson cycle was explained. We see the history of two general oceanic domains. One starts to open in the Triassic, and we have the first part of the closure in the Jurassic and the final closure later than in the Cretaceous to the Paleogene. And another system is a little bit northward directed. It starts to open in the Jurassic and closes finally in the end Paleogene, Neogene. So we have on one side the Neothetys evolution. This is the name of this oceanic domain, and we have the, one part of the Atlantic system. We name it Alpine Atlantic. Okay, you find also different names in the literature. And now it's crucial on the right side, you have a simplified stratigraphic column by that, and you see that some parts are lighter and some parts are darker. If you go in shallow water areas or in continental areas, continental organisms, they are not recorded in the sediments. Shallow water is also a problem because you have a lot of missing parts in the sedimentological record. So sometimes 100,000, 200,000 years are missing in the documentation. This is quite normal because we have sea level changes. The depositional realm is not underwater, so you cannot record. You cannot deposit sediments, and therefore it's simply missing or eroded. But in the open shelves, in the deeper water areas, we have more or less a continuous situation and a continuous deposition. And there we see changes. And now we have to find the filter which sedimentary rocks are really indicative to record changes. And by this you can filter, very important are organisms who produce carbonate. Carbonate producers, especially in the Paleozoic and in the Mesozoic. In the Cretaceous we have a new world, in fact. We have also planktonic carbonate builders. Carbonate production is more or less restricted to shallow water areas. So practically reefs, if you want to say. And this is a very sensitive depositional realm, because if you affect shallow water realms where all these organisms are living and you pollute somehow the depositional environment, they will try to escape if they can. And some cannot escape. If you are a coral, for example, you're living in the colony. You are sessile. Then you cannot move. An algae, it's sessile. You cannot move. So if the area is polluted, what is the only chance what you have? You can die. If you are a gastropod or something, you can try to escape and run away and find a better place. And therefore, exactly this is what we observe, but the main carbonate producers are exactly the sessile organisms. And if they have a nice environment, if it's warm, let's say subtropical or something, they enjoy their life and produce enormous amount of carbonate. And then, okay, you have the normal sea level changes, you have storms, whatever you want, and you have a backflow, and all what is too much produced, in fact, organisms die, this is normal life cycle, and a bivalve shell is, in fact, when the bivalve is not living anymore, waste. Also a dead coral, a dead algae is waste. But luckily, we have the wave power, we have the energy of the water, and this removes all these waste and transported it into the open shelf, where we have space. And therefore, we record practically a nice life cycle. In the shallow water domain, we see in the waste deposited in the open shelf. But if this shallow water area is now affected by some pollution, then we see, okay, no export of carbonate anymore, and the composition of the sediment is changing. And only planktonic organisms produce practically now the biogenic sediments. And most critical and most important are definitively quartz-producing organisms, siliceous organisms. And exactly this we see here in this column, the change from carbonate to siliceous sedimentary rocks. And therefore, if we have the change, we see definitively also global changes, and we can date them how fast they were. And therefore, this is very important. Okay, we come to the next. So these indicative other organisms, for example, here the conodonts, they give a very, very fine and exact stratigraphy, age ranges. Here our crucial organisms, the radiolarians, also they are very, very good and very exact for biostratigraphy. In the shallow water area, you have, for example, algae, foraminifera, and also the open marine ammonites. With all them, you can date the different sedimentary rocks in the shallow and in the deeper marine environments very precisely. And to correlate also shallow marine deposition with deep water deposition, because as I told you, material from the shallow water is transported to the open shelf, and therefore you can correlate very well the shallow water realms with the deep water realms. And if we look in detail, I will not go to explain you every formation, how we name it, but we see in our evolution several shallow water carbonate production time intervals. One is definitively in the lower part of this column, then we have one in the central, one in the upper, and one in the uppermost part. So in the Triassic, we can distinguish 3 time intervals of shallow water carbonate production, and in the Jurassic, at least 2 different ones. The red arrows show definitively these big mass extinctions, the Permian-Triassic one at the base and the Triassic-Jurassic one in the middle. In the middle, you see also the reconstruction of such a carbonate platform, how it evolves over tens of million years. Shallow water cycles and deep water cycles, correlation with the cyclicity of the different global change and faunal turnovers. But you see also 2 yellow arrows, and they are not recorded in these overall what you find everywhere as extinction events and turnovers, but they are also, you can recognize them practically worldwide, and they have a very, very special importance. Some are really global, some are over-regional. And they fit relatively exactly also with our plate tectonic cycle. We have at the beginning where we have this first yellow arrow. In our area, the opening of this oceanic realm, then is something what is still a little bit enigmatic. This is this yellow the second yellow arrow in the Carnian. This is maybe the most important turnover in the Mesozoic, because after this second yellow arrow in the middle Carnian evolves practically our modern world. After this extinction event, the different kind of plankton, especially the calcareous plankton, starts to evolve, which is then responsible for our modern oceanic geochemistry. This was before not available, and then it starts definitively with that evolution. Okay? Yes.
Can you just shortly explain how we recalculate this extinction rate? Just for
the calculation of the extinction rate is also a problem. The classical calculation of the extinction rate is based on the extinction of family or genera. And by this is also a problem because paleontologists, we are not biologists, and different paleontologists are splitting or not splitting, unify or not. And then it's statistics. Normally, you should calculate on the base of the extinction of species, But in fact, this is problematic because some define the species on the population, on the variability, other paleontological split. This is one point. And then they calculate on this general family level practically how many percentage die out. But the problem is if you see this calculation of the big five, but if you calculate it differently, how many general and total die out and not in statistic way, then you see the most important is this Permian-Triassic one, where practically 75, 80% or more, or 90%? More than 90. I don't count about the numbers because I calculated differently. Then you see you have practically a curve coming from the Paleozoic, from the Cambrian, and this goes in the Paleozoic down in cycles. And then it reached the Paleozoic fauna at the end Permian practically a minimum. So if you calculate in the mass, then you see that the Ordovician mass extinction, much more genera and families die out as at the Permian-Triassic. And then you have the Mesozoic fauna and the modern, and you have the curve in the other direction. So you have to calculate the amplitude and not to count the number. So it depends how you count. Popular is now to count in that way. But you can count also in a different way. Important is to recognize a turnover and to find the reason why we have a turnover. And always these statistics, how much, and this is in fashion, you know, a lot of things are in fashion, but what is the meaning of what is in fashion sometimes? Okay? In a moment, we can go later into more details, because this is a little bit tricky. Coming to the next. Sea level changes. We always discuss about sea level changes. Sea level changes are one very important thing to recognize. Flooding events, shallow water areas, they are in several amplitudes. Normally, this needs a relatively long time span. Sea level can rise and fall and has different reasons, and one reason is definitively climate change. And if the climate gets warmer, the sea level will rise. 10, 20 meters is normal by that. If you have an exceptional time as the time we are living in Ice Age, then we can have an extreme amplitude. As we know, in the last 11,000 years, our sea level was rising more than 100 meters. This is also an exceptional situation for the biosphere. But this is relatively untypical and only happens during ice ages in the Earth history. But important is, if we have a warmer climate, a greenhouse, Earth, then a lot of areas get flooded, especially shallow shelf areas. We get generally even warmer climate, and the carbonate producers enjoy their life because they have an enormous amount of space where they can grow. And this means rising sea level, warmer climate, greenhouse Earth, classical name, means enormous amount of carbonate production and enormous amount of carbonate export to the shelf. If the sea level goes down, then definitively all these environmental areas where the shallow water carbonate producers are living is very reduced. They cannot produce carbonate in this amount anymore, and this we see also in the sedimentological record in the open shelf. Careful, this is completely different from this sea level curve that we have the different system tracts defined of the siliciclastic system. And the siliciclastic system is working opposite. And by this we have to recognize some sediments are transported from a continent by weathering, and other sedimentary rocks are produced by organisms. And if we want to record and to understand the system, we can only go to biogenic sediments and not to the siliciclastics. So this means definitively what are the main producers and what are the most typical sediments practically everywhere. These are carbonates and silicious sedimentary rocks, and these are predominantly radiolarites. And the main players, the radiolarians and the shallow water producers we have recognized. So this high sea level and what we name higher carbonate production, the high stand shedding, is one of the very, very important tools to recognize such changes in the Earth history. Okay, we go to the next. If we look definitively in our area, we see, okay, this is also the Wilson cycle, the lower part of the stratigraphic column, the early Triassic and a little bit of the middle Triassic is the Graben stage. At the end, the Graben get flooded, shallow water epicontinental sea, relatively warm subtropical climate, and very, very nice carbonate production area. And then comes the continental breakup. The Neotethys ocean starts to form. Narrow ocean, a lot of volcanism, and this means also volcanic activity in a narrow ocean, not adjacent and not connected to other oceanic domains. This means pollution. Pollution of this young oceanic domain, ocean acidification, and now we can back to our algae and come back to our sessile carbonate producers. They cannot run away. They are affected by ocean acidification and they die out. And this means, by this breakup, juvenile ocean, we see here a turnover in the record, and all this shallow water production stopped and was replaced by condensed sedimentation and in part silicious sedimentation. But if you look a little bit closer, also this event which affected our area, you can trace in an over-regional manner and partly global. Not overall, in some areas you have a refugium, where some of these shallow water producers, shallow water carbonate producers survived, but anyhow we need a recovery phase. We have intense volcanism in our area, and in fact then we see that we need several million years that the carbonate producers, the shallow water carbonate producers came back. And they came back in the latest Lavinian, early Carnian, and then the first carbonate, shallow water carbonate platform cycle appeared with an enormous amount of export of the carbonate. This is the first you see, again epicontinental carbonates, then silicious sedimentary rocks, then this short-living platform, and then came this global turnover, again silicious sedimentary rocks, again a recovery phase of 5–6 million years, and then starts a long-lasting evolution of shallow water carbonate platforms, more than 25 million years. They were productive, affected by a lot of sea level changes, a lot of climate changes, but they were producing 25 million years and get not affected. Okay, they decrease a little bit in the productivity in cases by sea level changes, and then comes the end of this platform cycle, the mass extinction at the Triassic-Jurassic boundary, and then this story of this shallow water evolution is practically over. Then a little bit recovery in the early Jurassic. The next platform evolved, the Litiotis platform after that, and then start the next plate tectonic cycle. This is related to the Pangea breakup, and also the northern oceanic domain starts to open. Anoxia, again, ocean acidification to Asian global turnover with an extinction event. But you see all is very well recorded in these open shelf sediments and the change of carbonate to silicious sedimentary rocks. If you look a little bit closer, the time is running very fast. look a little bit for these different extinctions. Here we reconstruction, how this continental breaker is also demonstrated in the topography and morphology of the different basins. You see on the left side some of the players producing carbonate. Classical are algae. They are always responsible for more than 50–60% of the whole carbonate production in shallow water areas. And these foraminifera are also good for age dating, and this situation here, how the morphology practically a typical unconformity related to tectonic events you can reconstruct through time and space, which you can do practically on the later shelf area. Okay, the next. We see after the recovery period of several million years, after this extinction, the next evolving carbonate platform. Some examples of this carbonate platform, you see a lot of organisms there, reef builders, and these are mainly microbial dominated, and sponges and stromatoporoids. So it's very specialized fauna with a little bit of Paleozoic character, not a modern character. And also, we see there is an extinction at the end. All this biosphere is hardly affected, but it also we see that we have tectonics. This platform get tilted during that time. And also then the deposition changed from carbonate to silicious rocks, and also siliciclastic from the hinterland came. So this is also a global change. On one hand, a large indigenous province, on the other hand, also a tectonic event. Even if we don't understand exactly what these tectonics mean, but we recognize this is practically everywhere. This tectonic event you can trace from China all over our Mediterranean area, and you see it also in the Baltic Sea. As I told you, this is one of the most important turnovers. There we change practically the old world to the new world. Next. A look on this long-living platform cycle at the end of the Triassic, 25 million years minimum, one of the largest platform cycles ever. You can say north-south direction, more than 1,000 kilometers. If you calculate it, maybe a little more, and east-west, so equator parallel distribution, nearly to 20,000 kilometers. So this means millions and millions of square kilometers at that time were covered by practically Bahama-type platforms. And you see, if you look for the organisms, completely different. There you have the first modern corals, the modern sponges, and also a lot of other modern organisms. Completely different to what we have seen 8 million years before in this platform cycle. And here on the left in this picture, you see that sea level changes, climate changes, for a short time practically not affect this carbonate production. In the lower part, you see this is a lagoonal sediment. If you go to the Bahamas or something like that, you can move there, normal, shallow water, ooids, and then sea level drop. Okay, the platform emerged, get eroded a little bit, and the carbonate solved. And then the next flooding, you see in the middle, there's a flooding sequence, a little bit more open marine, and then the progradation of the next reef. So always sea level changes, shortly interruption, a lag and deposition, a gap, time which is not recorded, and then next cycle. And this you can trace in this platform a lot of times. So sea level changes, in fact, don't affect such a carbonate production area, not very much. So we need some other reasons if we want to stop the shallow water carbonate production. And the next one, short to show you, this Toarcian black shell event. You see on the right side the typical organisms, also completely different than what we have seen in the late Triassic. This Litiotis type, full of these reef-building bivalves. And then at the end, when this platform dies, you have a classical, what you see very often, a black shale event in the open sea. Totally dead sediment, laminated, no life at the sea bottom, so nobody dig in the sediment, and therefore you have this nice lamination, and you have organic rich sediments. But if you look closer, inside you see in these black shells there are radiolarians inside, because they live planktonic and they survive. So in the open sea, in several tens of meters water depth, 200-meter water depth, this plankton is surviving. But the shallow water area is highly affected. If we come to the next, we see this early Cretaceous extinction, and then I will not bother you anymore with much more extinction events, what we have recorded in our area. You see the next collapse of the carbonate system in the early Cretaceous, and you see also by the figured organisms, it's again different. So every mass extinction and every change and die on death of the different organisms open the space for new organisms which can evolve into the free ecological niches. Next. If we compare this definitively with the plate tectonic history, focused on our area, you see this northern oceanic domain, the Alpine Atlantic, and you see here this Neotethys ocean. And after this ophiolite abduction in the Jurassic, the western part remain open. This is practically what you name the Vardar Ocean. And okay, we have the opening in the middle Triassic, then the long-living passive continental margin with several shallow water carbonate platform evolution stages affected by several changes. And then in the middle Jurassic starts to close one part of the ocean. Ophiolite abduction starts, a lot of volcanism, not very nice for the environment. And this you can practically trace all over this realm, so the whole eastern Mediterranean area is affected by this event. And after this ophiolite abduction starts, we form a next shallow water carbonate platform on top of them. This we can see here, this late Jurassic, early Cretaceous evolution with the evolution of huge carbonate platform on top of the abducted ophiolites and also of the affected lower continental plate with some remaining deep water basins. Important is then later starts mountain uplift and unroofing. This carbonate platform is mainly destroyed and eroded. But anyhow, at the end of this cycle, when it comes also to the collapse of this platform in the early Cretaceous by the next global change. So these extinction events, how they look like if you look for the sedimentary rocks. Here's some examples. On the left side, you have such a shallow water production area, and then you see below nice different grains, different organisms, full of life, and then above you see only microbe layers and not destroyed by perturbation sediments, fine-grained and, so then it's dead. This is how it looks under the microscope in the fin section. Life cycle, life is flowering in the lower part, and then bye-bye, global change, extinction. And on the right side, there are some examples of these radiolarites also in the open marine, how they look like. Then you see these fine-grained layers, and these are products of volcanic activity, volcanic ashes, which pollute more or less the depositional environment. If we summarize it, then we see, okay, in our different areas, okay, Permian-Triassic boundary, one of the classic. starts also definitively with the Graben stage of our oceanic domain, so also overlapped by plate tectonic. And then we have a recovery phase by that, and then we see, by the opening, we get the mass extinction, ocean acidification, and extinction of these shallow water organisms. Then we have a period of recovery until the carbonate producers come back of several million years. 5 million years we need. It's permanently volcanic activity in our area. And then after recovery phase, the first carbonate platform evolves. But interestingly, you see, there are these red bars inside. The volcanic activity continues, and this doesn't affect, even if it's directly very near to this carbonate platform, has no effect on the carbonate production. If we look for the next one, the early Carnian, after this evolution, we see also this is in the recovery and the flowering phase, and then came the early Carnian extinction. This should be related to a large indigenous province. This is a classical interpretation, but if you date it exactly and go more in the correlation of the dating, then you see that this large indigenous province starts a little later. It's 300,000 years younger. And ongoing volcanism hampers then more or less definitively the recovery phase, and then we came to this long-lasting carbonate platform evolution in the late Triassic. If we have come to the next extinction at the Triassic-Jurassic boundary, we see a completely different evolution. We see that we have in the late Triassic, in different phases, a stepwise extinction. So in these 25 million years, we can record in the whole sedimentary sequence that the system is affected by several not very important but recognizable extinction events. And at the end, at the Triassic-Jurassic boundary, this is only practically the final shot. And this led to this, one of the big mass extinctions. Okay, then again, recovery phase, and then we see to the next platform cycle, it starts to evolve, and in the early Jurassic, we see the same. Also there, in the early Jurassic, after a recovery phase, we see to the next mass extinction, a stepwise extinction. This is not an abrupt change. This has forerunners. And this is completely different if you go in the Paleozoic, you see the same. Sometimes abrupt, rapidly, and sometimes stepwise. In our area, you see then, after this early Jurassic extinction, we have a very, very long time of recovering. Global, we have also for our 5-6 million years, but in our area, enormous amount of volcanism, ophiolite abduction, a lot of tectonics, and we need more than 20 million years recovery until the shallow water producers are back. And in the early Cretaceous, again, to the final end, a stepwise extinction, and then the recovery phase. So differences, and also if you correlate it with that, you see sometimes large indigenous provinces start a little later. Sometimes they correlate quite well, like in the Triassian, but it seems that these large indigenous provinces, which are active for a long time, some few million years, hamper practically also the recovery of the system by the pollution. They are probably not alone responsible for that, but they practically hamper the recovery and that it's longer lasting. A better correlation is also with plate tectonic cycle, and it seems that several effects work in concert. Then we came really to the global changes. But you see by this, a lot of things are still not fully understood. But one thing is fully understood if we look the last slide, that we are in a good way. Thank you.
Well, thank you very, very much for this partly too comprehensive presentation. Now we are facing to an interesting discussion, which will I start with a simple question, but I would like to ask you to be less comprehensive in your answers, so just to be short, to the point, concise. It's possible? Because my first question will be referring to, yes, it will be very short. Just define this time distinction between these long-term and short-term events. You never mentioned that, but I think it is, or just confirm that I think it is millions of years when we speak about plate tectonics, and some less than million years or whatever if we speak about short events. Because I know when we speak about meteorites, but then we speak about large igneous provinces, which of course last much longer. So what is your answer in that definition of the time scales?
Okay. Usually you will read that people wrote something around 3 to 4 million years, but it's not actually really time, because we have some events which happened during the 10,000 years. It means if...
You are speaking about short or long-term events?
If you ask about the time for events, when we are speaking about... when we spoke about mass extinction, for us, it's very important the number of species which died and the time, okay? And that's time, if we spoke about that time, usually it's, we talking about 3 millions, but I told you it sometimes happened really in some shorter time, if you ask.
Okay.
To be also a little bit precise, for several extinctions I presented, like the Anisian or the Carnian, we have meanwhile an age resolution better than 10,000 years. So this is
okay, so I would like now to encourage the audience to put some questions, to be brave. Christina?
Yes. Thank you. I appreciate your acceptance to participate to this event, despite your overloading by the lectures at the university. And it is nice that geology is today maybe closer to our society. And I need your opinion about the knowledge of geology, if it is enough applied and recognized by the society or not. What can we do to make geology more visible? We are faced panic in the society, and some simple geological data can explain some dramatic events, including these global changes.
Several questions in one question. First short answer to the first part of your question is, okay, everybody use everything everywhere. And okay, nobody is questioning where is coming practically all what we use every day. Nobody asks if you open the pipe and take the water and whatever. In fact, all this is based on somebody who has searched for it and geosciences. This is part of our normal life, and geoscientists do the job. And to coming to the second part of the question, can this help to explain definitively what is ongoing? If we understand the geological past, we have a chance to understand the future. And if we understand why we have such mass extinctions, what are the reasons, what can be the reasons, how fast they are ongoing, how long is the recovery period, maybe we'll understand what happens in the moment.
Thank you.
At the end, it means also that geoscientists, which are now practically a little bit in the shadow everywhere, but in fact, if we look a little bit closer for all what is practically on the surface of our Earth, and to understand the system Earth in general, what we use everywhere, every day, every hour, every second, it needs definitively that somebody who is understanding the system Earth in general needs to also to discuss practically in every small town, in every district, and to say, okay, this is maybe better to do, maybe to protect, in this case, a little bit maybe the groundwater which we daily use, and maybe also with the vegetation, take a little bit care that no mass transport events affect the areas and no damage by this. But classical things, which we daily mistakes by the people because they simply don't know. Okay, nothing again, you cannot know because if you have not learned it, you cannot know. I'm also not able to produce a smartphone because I don't know how to do it, because I have not learned it. But for geoscientists and for the nature and for everything, everybody is thinking he knows what to do. No, don't know because not learned it. Geoscientists have done it. Okay?
Thank you. Yes, please.
Thank you. First of all, thank you very much to CPN and to the panelists for coming and for making this possible and for cooperating with us as Austrian Cultural Forum for the organization of this great series of debates on scientific topics. And I would also like to ask a question. Like we are all dealing with global change, like global warming, climate change. These issues are very prominent. And can geology give an answer as to what extent humankind is responsible for these events?
Thank you very much. Yes, this should be a part of your presentation because I saw in your abstract that you have some final lines dealing with global warming in the relationship with the Industrial Revolution. So you put that on as the last slide, but I think it will be contained in this answer. Please.
Yeah, we are surely that we now have really some data from sediments which show that we really done a big impact. And just to inform you, maybe you don't know that geologists reject Anthropocene as a new geological epoch. It's happened at the end of last month. I think it was 24 April. It was meeting of International Union of Geological Sciences, and it's submission for partner stratigraphy. Member of that subcommission voted and rejected. But we are sure that we really have maybe from the middle of last centuries, it was proposed date for beginning of Anthropocene 1952. It means that we really have from that moment in sediments residues of testing atomic bomb. Yeah. But also we think that it's biggest problem nanoplastic. That's
okay. So.
We also found it that in sediments. Actually, it was happened in Ulcin. We visited some mites and profile. It was really incredible that I said it could be type locality for the Anthropocene because it's near the swimming part and it's some kind of walking path. And how people clean that, you can see in sediments really cans and pieces of plastic, like we found it fossils in sediments for the these Mesozoic sediments. Okay.
Thank you. So if I may add, so we may be sure that we have some impact that produced we as human beings. But on the other hand, in this presentation, we were able to see a range of events that were driven by the plate tectonics in different scales, and therefore I think we have to a bit refine our terminology which are related to nature or environment protection, because when we read or see that they write down, for example, during some demonstrations that save our planet, that is exactly not true. We are thinking about biosphere most of all, or system Earth, not about the planet, because the planet is much larger and much stronger than we are. So this recovery that was possible to occur after the extinction events means that our planet will recover.
I totally agree.
This is by all means true, but we will not appear again.
Yeah, but sometimes...
So save us, please, not the planet.
That's almost... But I agree with you, that's the true. Most of geologists don't like that save the planet, but also people must have knowledge about influence. It means planet will survive anyhow, but what will happen with us?
More questions? Yes?
Thank you. Well, then the conclusion would be that we shouldn't worry about the planet. After us, it would fully recover. So, first of all, thank you so much for your presentation, and of course, colleagues from the Austrian Cultural Forum for bringing this event to the CPN. However, based on our local perspectives here, and also reflecting on, you mentioned this huge event last week in Vienna, this huge geological union conference, if I'm right. And I heard, because one of our colleagues, she was presenting there. She told us it was an amazing event that they gathered like thousands of people, 20,000 people, so wonderful. But here in Serbia, unfortunately, I think that geology isn't that popular, or to be honest, isn't popular at all. So can we maybe identify some measures to increase the visibility of geology? And do you know for some maybe concepts, approaches, methodologies in order to attract younger audiences towards it, in order to increase the enrollment at the faculty, and also maybe to link better geological research, amazing things you are doing with practical stuff, of course, in the context of climate changes, but also in some current challenges that we are facing on the Earth. Thank you.
Hans-Jirgen? No, this is a question about
Serbia. That's... So you don't have such problems in Austria? I doubt it. You are going to exploit lithium.
Yeah, because it's not just problem with Serbia, it's generally a problem. If you ask, really we try, we promote, we give some science lecture and work with kids from schools, but it's really general problem. It means decreasing is everywhere, not just, maybe not in China, maybe. But the Japanese also have decreasing with,
Okay.
But, maybe we don't know the way. I think it's also a problem because it's new generation, and for them maybe the kind of media which we use is not correct, yeah.
If I may add, so if you were referring to the recent developments, so that this popularity of geology has its roots and reasons, so it is very clear that it was related to an eco-populism that was developed here, and one of the victims was geology, because some kind of very reasonable fear or concern to protect the environment was related to some kind of spreading the fear out of all limits and without any responsibility. Because if I want to spread the fear, then it is very easy. If I want to counterbalance it, it is difficult, very difficult. So you cannot do it with knowledge in Serbia for the moment. No. You can do it only with force, but we don't have such force. So we are facing with the lack of students, which is not related only for that. It is general problem. And you cannot deal and counterbalance that only with PR things or commercials or whatever. To go to the high schools and promote geology, no. Forget it.
Okay, and finally, I have to add one general problem. This is because this is a problem of our modern society. Our modern society is technology-oriented. And it's oriented to have for everything something what you can measure and put into the statistics. Output. The administration wants to have numbers. And every science, what needs a little time to come to a result, cannot produce this amount of output. Numbers. Yeah, as technology. If you have a small innovation, maybe you construct a chip or something, then every micrometer you make it smaller is an innovation. And this you can count. And at the end, in 5 years, if you work with a team, you have 50 steps. And these are 50 points for the administration. And also you have 50 patents and you have 50 publications. If we need for rock sample and to achieve at the end a result, we need a long time. Laboratory process, then analysis, then interpretation, and then at the end one sample is not enough. Then to find the proper rock in the field. So you have first to go and to look, and not every sample is positive. This needs time. Sometimes you have to repeat. And this means at the end our statistic is negative. Has to be negative for the administration, because we cannot produce these numbers. And this means definitively if you calculate everything with such measurements and in such numbers, and with such statistic methods by the administration, they show definitively what are all these scientific disciplines, and geoscience is one of these. They say they are not productive, what they are doing all the time. And this means they reduce all these disciplines everywhere in the world, which cannot produce these numbers, the money for research. They reduce the available positions, they reduce the staff at the universities. This means definitively lower quality of education and of teaching, because also to bring a youngster of our discipline and also several others to a certain level that he knows to go in the field and to bring the right sample from the field, to analyze it and came to a result. This needs time. This needs time, because it's experience. But this is against our measurement, what we are doing in a technology-oriented world. And therefore, we are practically invisible now, but they expect that we are doing in the background everything. Everybody expects of us that everybody in the world has drinking water of high quality coming out of the pipe. Everybody expects of us that enough electricity is available. Everybody expects that every technology is available and can be used everywhere. But there is coming the material from, there are coming all the raw materials from, for every building, for everything what we every day use. Some geoscientist was going out in the field under bad conditions, maybe creeping in the mud, affected by ice balls, by thunderstorms and whatever, and took practically under the risk of his life, creeping through snakes and scorpions and whatever, and take the sample and find it what we daily use.
Don't be angry with us, we agree with
no, only to state it because I see it's recorded and maybe somebody will see it.
Hi, Professor. Yeah. Still standing on the existing protocol. Thank you so much for the exposition. From the last slide, I could see the scenarios mentioned there, the emission and all that. And from the exposition, I got that we could have natural and human factors that could affect our world and the environment. So my question is the human factor significant compared to the natural factor that is adding to our carbonate system? And how can we measure the two? Because one of our colleagues asked, like you said, if we cannot control it, then we don't have to bother about our environment. But the thing is, we still have human factors. That's from the last slide, we can see those wastes being put in this water body, and all that can affect the carbonate system. So to what extent, how can we calculate the effect of human factor and the effect of natural disaster and occurrences? And how can we separate them to know at what extent our world is being affected and from what extent can we help?
Thank you. So I think we already agreed that we have that impact, but only maybe a few words more how to distinguish them. I think they are distinguished in time scale, but you have some measurements which are very straightforward. If you have some more than around 40 ppb of CO2 and a steady state increase from the beginning of the Industrial Revolution, if it continues to increase up to thousands of ppb, then and above that, it means that there will be no ice on Earth. So please continue, Emke.
Be a little bit harder and a little bit more direct. You say always answer direct and to be specific. Or to answer your question, go to the coastal area and maybe you have available data on a normal beach. Take the normal sand in your hand and count the grains. And in a classical environment 30 years ago, and if you count the grains, then you see 60% quartz and 35% carbonate grains and 5% something. And if you make it systematically all 5 years, and if you go on the same beach today, then you find 85% quartz and 12% carbonate grains, and the rest is also something. And by this you see definitively you can measure the impact what we have on the biosphere, especially on the carbonate production system. And you said now we measure it also in the different sediments, in the different isotopes, and in the different metals what we see. And if we really recognize our impact exactly in the sediment everywhere, and not only in specific areas where we have isolated and smaller oceanic basins, if we recognize it everywhere, that we can measure it also statistically, I can tell you then it's too late. then we are over the turning point.
Not for wine, it is okay. For wine for tomorrow, for today.
Then it's no need to define anymore the Anthropocene. Then we will have the Quaternary and Quaternary to the next system. Somebody will invent in 10 or 20 million years. We don't know the name, and then they say, okay, this impact is the Anthropocene.
Very well, thank you. Again, you are not satisfied with it. Just, you don't understand. Probably you want to hear something specific about difference between natural and human factors.
Exactly. Now I got from the response, I got an insight of what the human factor is actually doing. Now, to what percentage can we accrue these two? The human factor and the natural factor, because we know the effects of plate tectonic, what causes it, how the carbon emission and all that. So to what extent and the duration can we accrue these effects to?
Maybe you are not going to get that answer this evening. I'm not that sure. But you, by all means, you cannot relate and correlate plate tectonic events and these kind of changes that correlate with human history. So that is just maybe the most simple. Or
yeah,
you want to...
I want to agree with you because our life is really short. If we compare with the Earth history, you know, if we put 4.6 billion years in 24 hours, it means Homo sapiens appears in the few last seconds. And it's really impossible to compare. For this, if you can understand what I want to say, that our human life is really short, few millions we are on this planet.
If I understand your questions correctly, you want to have a forecast how much time we have to produce a waste and to pollute the area. If we would know that, it would be great. But I think no model and nobody can tell you. We only see there's a rapid change. And at that moment, we will know it. How long it lasted, then it's too late. This is the answer. Nobody can tell you.
And it is always possible to continue in bilateral form, just to find and to speak with Hans-Jirgen in private. Well, do you have more questions? I wanted to know exactly what large igneous provinces you were referring to, because you always put large igneous province, but presumably they were not on the same distance from the region you were speaking about. Of course not. So they were somewhere in the world, because I think you should clarify that in a couple of sentences, because that is not, I mean, the people are not familiar with the igneous provinces. Just take the microphone and say. You were referring to what? Okay. So it was irrespective of that, how, I mean, you know, whether it was 5,000 kilometers far away from the generator. Okay. Oh, but it will, yes, good. In your next presentation, you put the names there, and then we can organize ourselves. Okay. Well, I was a bit offensive, so you can continue in that manner. Oh, yes?
If I can just make things a bit around, yeah. What would be the status of biosphere without our impact in the last 200 years? Can you make this kind of estimation? So, what would be the situation now regarding environment, at the planet and biosphere without human negative impact in the last 200 or 300 years?
It's really impossible to answer. Yeah, it's really hard answer. Okay, we know that we are from the last maybe 20 years, we are really hurry up with that story. And from 1990, last century, it's more visible, but it's really impossible to say. It's never know really how should be. Yeah, I know that people like that, but we are on the opposite side. Geologists don't like that. You know, most of us don't like to look any kind of, you know, National Geographic, because it's everything, it must be the most, you know, something very special, and also that kind of forecast. It's impossible. We can explain how it's happened in the past, and we know today also situation, we know where we have oceans, where we have continents, how things is today, but forecast is really impossible.
I have one possible answer to offer, maybe not 100% ironical, but more or less. So we would have had a lack of hundreds of thousands of publications that appear every year regarding of the environmental problems related to the human impact. So this global change, scientific papers that appear every day, that is an enormous number. So in that case, you are not satisfied with that?
No,
answer.
I'm
Good.
not satisfied. You never know if you want to have projects. Sometimes you will write exactly what is good today to catch money for that project. Sometimes it's not really that you can agree with all data which they publish. I must be honest, sorry.
Well, do we have more interest for questions or not? We are now approaching an hour and a half, so it is a nice time. It was a nice time for conversation. We saw a nice presentation and then had a thorough discussion. And if is all, then I can close this event. With my great pleasure, I thank you very much for being today with us. And our invited speakers are also very appreciated to be with us today. You look a bit disappointed, Hans-Jirgen. No? Okay, then I am fully satisfied. Thank you very much again, and I also thank to the organizers, to CNP, and to the Austrian Embassy Cultural Forum. And CIPUS, of course. Thank you. Bye.